So I was trying to think of how to introduce Dan, and this is actually a really challenging job because Dan does so many different things. He's probably most famous for his Python package MC, which all of us have used. Raise your hand if you used MC. Yep. But Dan overall is an expert in statistics and data analysis and is interested in any interesting data analysis problem. Most recently, his focus has been a lot on exoplanets and searching for small signals in time series, and I think we'll hear about that today. So without further ado, let's welcome Dan.
I'm getting text messages from Dan D'Orazio right now saying that he hopes that my phone is on silent because, thank you, Laura, and thanks everyone for having me here. It's been a while since I've been here, but I always have a great time when I come to visit. So, all right. So to start off, I would also like to introduce myself, just because, in my own words, because that'll set the context for the kinds of things that I want to talk about today. And so I'm Dan. I live in New York, and I spend most of my life writing software, and that's more or less my job now. And on the internet, this is where I live most of the time. And this is GitHub, which probably most people have heard of before, but it'll come up a few times, so I just wanted to mention that GitHub is a website where you can host open source software, but it also has some sort of social features that will come up again a little later on. So it's a place where you share code and discuss code and develop code in the open, and maybe papers too. And then I wanted to spend just a second talking about where I work, because we're kind of the new kids on the block, and so I just wanted to, I'm contractually obligated. No, I'm really not. But so I work at the Center for Computational Astrophysics at the Flatiron Institute, which is in New York City. We're called the Flatiron Institute because we're not in this building, but just down the street from it, thankfully. I bet it's not a very nice building to work in. Yeah, we're just 2 blocks down the street there, and we're a pretty new privately funded institute. We're not associated with any universities. We're part of the Simons Foundation. And if anyone's looking for jobs, we have about 10 postdoc fellowships every year that are really awesome. And I'm not just saying that because I'm biased. They're actually they're pretty great positions, and so everyone should think about applying for those and talk to me if you have any questions. Okay, done with the advertising. So the title that I gave was something like Data-Driven Discovery in the Astronomical Time Domain, and now that you're all here, I can change the title to something that's more like what I want to talk about, which might, we'll see. So I want to talk about sort of some of my favorite things and my day-to-day research. I'm going to talk about noise models, I'm going to talk about algorithms, and I'm going to talk about open development and open source scientific software. These are all topics that we'll touch on. So my goal is to discuss all of these things that are in my new title, and I'm going to motivate them using time domain astronomy, so the original title wasn't a complete lie. But some of the things that I want to make sure that I highlight are sort of the benefits in my career of interdisciplinary collaboration and sort of open development practices, but also things as sort of mundane as good documentation and things like that. Okay, so we'll get there. So, time domain astronomy, as I'm sure we all know, is it's all the rage these days. You measure something as a function of time, where that something might be something like that. I mostly work in exoplanets, and so that's one example of a recent success of time domain astronomy. One example of that success is a plot like this that I made a while ago. It's a little out of date, but sort of you can see over the past couple of years there have been lots of discoveries of new exoplanets, and that's really cool. Lots of news and press and stuff like that. Whoa, geez. Okay, but who cares? We find lots of planets. That's cool, but so what? And one thing that I wanted to mention is that Kepler, which was sort of one of the major drivers behind all of these discoveries, was specifically designed as a statistical mission with the goal of understanding the populations and understanding the rate and distribution of exoplanets throughout the galaxy. Here's a plot of some of the discoveries that Kepler made. Here we have the orbital period along the x-axis and the actual radius of the planet. And plots, I'm sure everyone's seen lots of plots like these, and we have learned tons of interesting things from plots like this, and we continue to learn all sorts of new things about physics and exoplanet populations from things like this. But just one thing that I wanted to point out for today's context is that if one of the things that you might be interested in learning from a plot like this is, what is the frequency of solar systems like ours? How common, how weird is it that we exist? And so I could overplot the solar system on this plot, these orange points down in the bottom corner here, and you can see that there isn't a lot of density down there. And that's not necessarily because we're super rare. Part of that is because our solar system is right at the detection limit of a survey like Kepler. And we can zoom out a little bit and show the rest of the solar system. And Kepler Super wasn't designed for finding these planets out here, but this is another example that sort of, again, right at the limit of detection is where a lot of the interesting things in our solar system live. And so the point that I wanted to make here is that we want to make sort of state-of-the-art discoveries at the limit of the at the detection limit. And if we want to make those kinds of discoveries, then we have to really push the techniques and develop new methods and things like that. We really need to push the boundaries. And a point that I wanted to make right here is that when you do this, when you're really pushing to the limit of your understanding and the limit of the methods, you often don't have a good training set in the sort of typical machine learning sense. And so a lot of what I'm going to talk about today, a lot of the methods that I'll talk about are informed by machine learning and computer science, but they're also they have added physics and things like that as a way to sort of improve the training set.
So,
yeah?
Just out of curiosity, with that last plot, so would you say that trend is just a sensitivity limit? It's not really a trend?
You mean down here?
Right. The fact that
Yep.
there's a trend.
Yeah. So these lines that I've drawn on here are representing the sensitivity. So those are curves of sort of roughly constant sensitivity. So there's also sort of a hard limit at this end, but this trend right here is mostly dominated by the detection. Yeah. Any other questions? Please interrupt me as we go. It's more fun if we can have a discussion. All right. So now that I've said all these things, I wanted to talk a little bit about. I've mostly worked on Kepler data, and I've looked at exoplanets through the transit method, and it's awesome. And I just wanted to sort of describe it a little bit. I'm sure lots of people have know everything about it already, but I just wanted to give some context here. So here's a picture of a star, and if we happened to be aliens outside of the solar system looking in at this star, and happened to be looking at exactly the right angle at exactly the right time when Jupiter transited, we would see something like this. We'd see Jupiter block out a little bit of the light of the sun, and we would see the sun get fainter for a couple of hours. And to scale, if we saw the Earth transit as well, it would look something like this. So that's, you can see it's a much smaller area that it's blocking, and so it's going to be a much smaller change in the brightness. Of course, as we all know, this is not at all the picture that you actually see when we look at other stars. We see something more like this, right here. So I don't know if you can see it, but there's one pixel in the center right here, and that's more what these really look like. So in fact, in sort of a perfect world, this is the 1D kind of information that you measure as, this is the transit method. This is how we discover planets. And so this is sort of the best case scenario of what you would see for Earth transiting the sun. You can see that the change in brightness is about 100 parts per million. So that's a very small change in brightness. It only lasts for half a day. And by definition, it only happens once a year. So there, all of those different aspects means that finding these things is pretty hard, and that sets certain constraints on the types of surveys that can measure transits. But another thing that I mentioned very briefly in passing that I just wanted to bring up is that there's also the geometric factor. So you have to be aligned at the right angle to actually see this, to ever even have a chance of detecting something like this. Even if you have the most precise detector in the world, you're going to need to get lucky to be looking at the right time at the right angle. And so here's a summary of all of those things that I was just saying. So you need to measure the brightness of your star outrageously precisely because you're looking for these tiny deviations. You have to deal with the geometric effect by looking at many different stars. You have to be looking at the right time, so you have to have a fairly high cadence. And because the orbital periods of some of the things that we might be interested in are long, you have to be looking at these stars for a long time to get them at the right time. And so this is exactly what Kepler was designed for. These are vaguely some of the stats. That's a picture of what Kepler looks like. Unfortunately, Kepler recently is retired, and we'll get to that in a minute. But it's a good old friend. So one thing. So all of this story is pretty nice. I talked a lot about all of the sort of issues with making sure that you're looking at the right time and getting precise measurements. But of course, the real world is more complicated than that. Here's some real data from Kepler. So here we're looking at about 3 months of data. And there's a ton of different stuff going on in this plot right here. First of all, there are 5 planets. I don't know if you can see them. Maybe some of our exoplanet friends can. But most of what you see is stellar variability in this particular example. So most of those trends are caused by the star, rotation, things like that. There's also effects of the spacecraft. So Kepler was super precise, but it also, it wobbled a little bit in its orbit. It had to move to downlink the data. So there's some systematics left over from the spacecraft. There's also just the standard noise introduced by making any measurement. You can see some of that. And then if you really squint, oh my gosh, I don't understand why that keeps happening. Let's do this carefully. If you really squint, you might be able to see some planets in here. Maybe. So I haven't actually checked if that's actually a planet. But anyways, so all that to say, there's sort of lots of different ingredients at work here. And so to sort of simplify things a little bit, I like to sort of draw out a schematic of all of the different ingredients that I think are going on. And so that looks a little something like this right here. So we have our observation that is some combination of these different effects. And most of what I'm going to talk about today is sort of methods for computing these different parts of this model right here. So these are the different ingredients that go into it. Now, one thing before we get into too many details that I wanted to mention is that one of the things that is was maybe obvious or maybe not, but with Kepler there's obviously a lot of auxiliary science results. And part of that comes from, you know, all of the reasons why the transit method is a hard way to study planets. And another way of putting that is that the transit signal that we're interested in is very sparse in the time domain. And so that means that there are a lot of measurements that don't tell you anything about the planet, but they tell you a heck of a lot about the star. And obviously there are tons of stars that were observed with Kepler that that don't have any don't have any transiting planets, and so so there's a lot that you can learn from those data. So just to sort of show that, here's a fairly short period transiting planet. This is all the Kepler data, and if we zoom in a little bit, you can see here. I've zoomed in. You can see a couple of transits, but really that's a tiny fraction of the total data that was collected for this. And so there's actually a ton of information in the rest of the light curve. So in this particular example, there are astroseismic oscillations, and you can learn a lot about the star from all the rest of those data. And so all this to say is that we don't just care about just the transit part of the schematic that I showed. There's lots of information in the other pieces, and that's something that will come up a little bit later as well. So we have this large data set. I said that Kepler has been retired, but we're not going to run out of data to analyze in this space anytime soon. There's K2 data that still has a lot of work left to be done there, and then tests. Word on the street is that the data are going to be released the day before Thanksgiving or something like that. So it's going to be really fun. So there's a lot of exciting stuff in the future. Okay, so this was sort of some of my motivation, and now we're going to sort of simultaneously go a bit more abstract and deep into the weeds, and so bear with me. So we have these huge data sets. We're going to continue getting these huge data sets. And so that begs the question, sort of what do we do with these data? And, as many people raise their hand to say that they've used MC before, so that means that it's a room full of good Bayesians. And so the only quantity of interest is this probability distribution right here. So everything that I do, and probably many things that many people in this room do, are quantified by a posterior probability that looks like this. This basically says what is the sort of distribution over physical parameters, or over the physics in your model, that are consistent with the data that you've observed. So this is sort of, this shouldn't be very controversial. So this is the fundamental quantity of interest. When you have a probability distribution like this, the only thing you're allowed to do are integrals, and we'll come to that a little bit later, but basically you're going to do a bunch of integrals of functions of physics weighted by this probability distribution right here. And then when it comes to actually computing the value of this probability, the sort of key quantity is generally the likelihood, which looks pretty similar, but basically the story here is that you want to write down some way of generating synthetic data sets given some set of physical parameters, or even better, evaluating the value of this function for a given data set and a given set of parameters. And so this times the likelihood, times a prior is proportional to the posterior probability, So when it comes down to it, basically all of science, and especially the science that I do, requires two things. It requires a way of doing integrals with that probability distribution that I showed before, and it requires some way of efficiently calculating that function that computes the likelihood of your data given some representation of your physics. Happy with that? Okay, good. I'm going to go on now to give three short examples of these two things from my work, and you'll see various themes develop throughout that. So the first example, I'm going to talk very briefly about methods for doing integrals. And if anyone comes to the lunch later, I'm going to talk about sort of more recent things in that space. And then I'm going to talk about two examples of different parts of the likelihood function and how to accurately and efficiently calculate them. So to start with, I'm going to talk about Markov chain Monte Carlo. Can I have a show of hands for how many people have used MCMC before? Yeah, great. So it's a pretty good showing. But I just wanted to I just want to give a very this particular part of the talk is pretty old news, but it sort of sets the stage for the other things that I want to talk about. So to start with, basically the idea behind Markov chain Monte Carlo is that in order to do integrals weighted by this probability distribution here, where I've totally changed notation, and this is the same thing as I had drawn on the earlier slide, that basically to do integrals in some high-dimensional space, often the easiest way to do that for many deep reasons is to generate samples from this probability distribution. And so that's sort of, that's the fundamental computation engine in all of this. So that sign means samples from. And then the key point is that in astronomy, this line right here in the center has a whole lot going on. So a lot of the time, this involves like your advisor's Fortran code, maybe like version 7 of whatever. So there's sort of a whole lot that goes into that, and there's a lot of there's physics that we care about. We want to interpret that physics, but there's also a lot of history. There's been a lot of work in developing efficient and good ways of calculating this, and so. So that's a key point that's going to be important here. And the one of the reasons why I mention that is that sort of the state of the art in MCMC methods requires that you compute derivatives of this function with respect to the parameters, and that can be hard if the function is your advisor's Fortran code. And so I have some ideas about that, and I'll talk about those at lunch, but we're not going to talk about that now. Now, if anyone has used MCMC before, then you might remember that or if anyone used MCMC back in the day, before it was cool, they might remember that it's pretty brittle. Like there are lots of different tuning parameters. The performance can be sensitive to the decisions that you make. And so to get good performance, you often have to very carefully tune your sampler for the specific problem that you're working on, or you have to simplify your model. So traditionally, that's what Bayesians have done. They've simplified their model so that they can do certain types of sampling with analytic relations and things like that. So it actually gave Bayesians a bad name. It's because we're making these stupid approximations that and so way back, I teamed up with some an applied mathematician at NYU during grad school, and we wrote this paper, and I think a few people in the room have used the code that goes with this paper. I don't know if anyone's read this paper, but a hilarious thing about this paper, so our idea was to make a method that didn't require too much tuning and didn't require your model to be simplified, didn't require gradients. And the thing that we came up with was, this is our entire algorithm. So this is what MC is. So it's super simple. But for whatever reason, it has become outrageously popular. Lots of people, I don't know if they read the paper, but they cite the paper, and a lot of people seem to be using this method. I don't think these are all saying that it's totally wrong. Some of them are, but this seems a little bit inconsistent, right? Like, sure, it was a good method for the reasons that I said, but it's super simple. Why has it become so popular? And I would say that sort of, obviously the usual things, like it was the right time, right place, and things like that. But another big part of it was because it was immediately released open source on GitHub with a sort of lenient license. And when it was published, it also came with good documentation. I think it's good documentation. And in particular, it had lots of code snippets with you can just copy and paste this and use this in your work. And so this was, as I said, old news. But I learned a lot from this particular example because even though it's an absolutely trivial algorithm, the implementation, I think, is the reason that people use it, because it's well documented and things like that. And I think that it's sort of underappreciated, and this can go a long way. And I'm hoping that I can show some other examples of that. Any questions? All right, so the next thing that I want to talk about is, I said that my next example was going to be about Gaussian processes. And in particular, I want to talk about scalable Gaussian processes, and you'll see why in a second. Gaussian processes are sort of widely used throughout astronomy, and they've been used a lot for exoplanets and things like that. But in my particular case, remember this is the sketch right here. We have our physics that at some level is the thing that we care about over here, and I'm going to talk a little bit more about how we actually compute these models. But then the rest of this can be written to good approximation or even exactly using a Gaussian process. And I'm not going to go into the details of what a Gaussian process is. That might be a conversation for another day. But basically, qualitatively, one way to think about it is that it's a model that describes the set of functions that your data set could be generated from, but it doesn't specify the value of that function. It specifies the covariant structure of that function. So in going back to this example right here, some of the parameters that might be part of your Gaussian process are things like the amplitude of this variability and the time scale, or the relevant time scales of this. So another way of thinking about this is that anything where you're parameterizing something by a power spectrum can also be written as a Gaussian process. So this is useful for modeling stellar variability. It's also useful for modeling the spacecraft instrumental effects, but I'm not going to talk about that today. But you can sort of understand why. We don't necessarily care about the phase of the stellar variability, but we might be interested in the specific time scales. For example, if we're doing astroseismology or something like that. Or here's one example where we have a rotating star, and one of the relevant time scales here is the rotation period, and that's something that you could measure using a Gaussian process. So lots of people have used Gaussian processes for lots of things, and it's cool, but of course the reason why I'm here is because there's a problem, and that problem is a computational problem, and that's that here is the computational cost of computing a Gaussian process model for some data set versus the number of data points in that data set. And you can see this gets pretty ugly. So this is, so in the limit of, there's some, I did this experiment with Python, and so there's some overhead for the small data sets. But as you get to large data sets, it scales as the cube of the number of data points. And so this isn't really going to reach to large data sets. And it isn't even going to reach to things like Kepler, where we have something like 70,000 observations per star. I mean, that's way out of the range. I mean, if we look at this plot again, that's not even on this plot. You know, it's going to take hours to compute a single evaluation, and probably there isn't enough RAM on my computer. You know, there are lots of reasons why, you know, something like this isn't going to work. And there have been sort of, you know, there has been work done on scalable Gaussian processes. This is, you know, in a very active field of research in applied math and computer science. But there wasn't anything that sort of worked for the types of problems I was interested in. So in grad school, I again partnered with some applied mathematicians at NYU. We published this paper. I think we submitted it like 3 years before it was accepted, because this is the way the world works outside of astronomy. You know, we're very lucky here that the turnarounds are so fast on these types of things. So they had an approximate method for solving Gaussian processes. Oh, one thing that I didn't mention before is that the reason why it scales as the cube of the number of data points is that you have to invert a matrix that's the size of your data set squared. And so that's sort of the fundamental limiting factor there. And so here they had a method that they were applying to other matrices that scaled as this, which is better than n. This is actually better than n squared, so that means that they're not even evaluating every element in the matrix. And that's why it's approximate. So we published this, and alongside this, we published a code called George that implemented this method and some other Gaussian process methods. And this has, again, become quite popular. So a lot of people use this, a lot within astronomy, but it's also been used quite widely in other fields. And again, part of that, you know, part of the reason why this paper got so much traction is because, I think, because of the documentation and the open source software that was released alongside. But unfortunately, this method was not fast enough for the types of problems that I wanted to work on. So I went back to the drawing board, still not fast enough. And so I went back to the drawing board and started collaborating. I continued collaboration with the first author of that paper that I showed before. And just last year, we published a paper that for a very specific type of Gaussian process model, I'll give you the details in a second, we get linear scaling. So you know, this is much better than cubed, and so if we want to scale this up to large data sets, then we get something that looks like this. So there's tons going on in this plot, so just let me break it down a little bit. This is the same as what we had before, number of data points, computational cost in seconds. This dashed line is the same experiment that we saw earlier for the naive calculations of the Gaussian process model. And then the different colored lines are versions of our algorithm applied to different complexities of kernel, so or different covariance functions. So remember I said that we have to parameterize the autocorrelation or power spectrum of the observations. And here, if you have a very simple covariance function, then you can evaluate it very quickly. And if you have a more complicated one, it gets harder. And it scales as the square of that parameter. But the key point here is that I now have the size of Kepler data included on this plot. And the scaling for all of these models is linear. So that's the same as computing chi-squared. And in fact, this blue line for a very simple model is only about a factor of 2 more expensive than evaluating just straight up chi-squared. So I just wanted to say so the restrictions are that we specifically designed this for 1D data sets, so things like a time series where you just have flux as a function of time or something like that. We are thinking about generalizations to it, but those don't exist yet. So right now you're restricted to problems where you have 1D data, but it can be unevenly spaced. So it can have missing data, it can have large and small gaps between observations, and all of that is good, but it just has to be 1D. There's also a specific choice of representation that you need to use for the covariance function, and a specific sort of set of power spectra that it can describe. Yeah, I'll talk about that in just a second. Oh, one last thing I wanted to say before I go on is, I don't know if there are any linear algebra nerds in the room, but all of this comes down to, like I said, solving, you want to invert a matrix, or solve a linear system. And the reason why this is fast is that the matrix that you get for these 1D systems with this specific choice of power spectrum, they're called semi-separable matrices. And we derived the Cholesky factorization, so the sort of classic method that you would use for computing these inverses. We derived that for this class of matrices. And so it hadn't been published anywhere, and it sort of has broad applicability. And people have started using this already outside of astronomy as well. So I wanted to comment on the sort of specific form of the power spectrum that you have to use, because the thing that I was really excited about with this method is that there's actually physical intuition behind the choice of power spectrum. So here's some Kepler data, and and you see the observations, then you see our model, our Gaussian process model, in the blue line going through the points. And the variability that you see here is all physics, because this is an astroseismically oscillating star. And so if I actually show you our posterior constraint on the power spectrum for these observations, it looks like this. And specifically, it's a mixture of stochastically driven, damped, simple harmonic oscillators. And so, we can actually interpret the parameters that we get out of this. We're not just sort of making up some power spectrum. And so under this physical model, we get very fast evaluations of the likelihood. And so I thought that was pretty exciting. Oh yeah, I was just going to show, this is if you compute the Lohm-Scargill periodogram for 4 years of Kepler data versus fitting our method just to a month of data. And so it's pretty cool. So again, naturally, this came with open source software that you should all use. And it's called Celerite. People have made fun of me for the name a little bit, so say Celerite. Yeah, you can find it on GitHub. It has a documentation. There's also an implementation in TensorFlow, so if there are machine learning people, that could be interesting. So that's all I wanted to say about scalable Gaussian processes. Any questions? Good. So the last example that I wanted to give was a fast and accurate way of computing the actual mean model in the schematic that I showed. So the shape of a transit or an occultation or a phase curve. And this is work that was led by Rodrigo Luger, who's an excellent postdoc fellow working at Flatiron. Right, so this was the sketch, and I'm going to talk about the thing on the left over there, how we compute things that look like that, and more generally. And so the basic idea, and this has been known for a long time, is that a star kind of looks like this, and there are several components that contribute to the limb darkening that looks like that. And if you want to compute the light curve for some object transiting this, then you can compute that as the sum of the contributions of the light curve from these different, from these representations of the star. And the star itself is a sum of these things, and the light curve is a sum of those contributions. And so that's been known for quite a long time. This is the quadratic limb darkening law. And now it's also been, ooh, geez, I gave away my punchline. So you can generalize this to higher order. And so that's also been known for a while, is that you can go to higher order. But the thing that Rodrigo realized is that these were actually just the m=0 spherical harmonics. And so you can actually generalize this more and include all of the spherical harmonics. And he worked out that you could analytically compute what the light curve would be for all of these, for every spherical harmonic. And then you add them together and you get the light curve that you want. So for example, you could represent a very realistic planet like that using just a few spherical harmonics. Here we're increasing the order of our approximation. Yes?
So once you go to spherical harmonics, it looks like you really can do, you're looking at something broader potentially, because if you really want to model the star, there's not only limb darkening, but there are gravity effects and, and other things that come into play. And so is it correct to say that what you're doing is you're sort of looking at, I don't know, the whole tamale in a sense?
Exactly.
Putting everything together?
That's exactly right. So the idea is that the math is the same for the star as it is for the planet, and so we can have rotating stars with spots on them, with limb darkening, and with everything coming in and out of view, and it's all the same math. And then the planet, you can also map your planet and have a rotating planet that's getting an occultation and a phase curve and all of these other kinds of things. So it's very broadly applicable. And in particular, in this specific example, here is the occultation light curve that you would get if you had some epic instrument, and it's the sum of all of these components that you see up here that are all calculated analytically. Here is, this is the light curve that you would get for the moon transiting the Earth. And then I needed to give a shout out to say that we're still not as fast as the local talent. So for the specific problem of computing the transit, we're competitive, but we're not quite there yet. This, of course, is Laura's Batman code that we're comparing to. But for the more general problem, we get, even for very high order spherical harmonics, we get very fast and accurate calculations of the light curve that you would expect for these things. So since Rodrigo and I have been working together, of course, he released this on GitHub with good documentation and an amazing logo. This is something that I've never, he really nailed it on that one. And this is called Starry. You should check it out if you want to compute any sort of more general light curves, then this could be a great thing. But this wasn't everything that I wanted to talk about this project. The other thing that I wanted to mention is sort of, while writing the paper, Rodrigo really took the open development aspects that I've been talking about so far to the next level. So here is a slide that he made where it's showing what happens. So we were writing the paper and developing the code in one repository on GitHub. And whenever we made a change to the paper or a change to the code, that we pushed that to GitHub, and then that got sent off to this service called Travis Continuous Integration Service. And on Travis, it ran all the tests to make sure that the code was doing the right things. But it also ran all of the code for every figure in the paper. So it actually generated all of the figures in the paper based on the specific version of the code. So at that time, this is what the figure looks like. And so that was really cool. And in particular, that enabled us to, when we have a figure, we have a little link in the caption that lets you see exactly the code at the right version number that was used to generate exactly that figure. And that's cool for lots of reasons, because this is sort of taking the like copy and paste aspect of documentation to the next level. You know, if there's a figure in the paper, that presumably is something that people might want to do in their own work. So another thing about this paper is that the math is really horrifying. And honestly, I'm not sure that I know all the details of everything that's going on, but one thing that was very cool is that as part of deriving all of this math, we used SymPy, which is an open source Python library like Mathematica, to go through and derive all of the equations that are in the paper. And each key equation has a link out of the equation to a notebook that goes through the derivation and proof of that equation. So no more of this, trying to reproduce someone's results and not being able to derive the equation that is obvious, right? We've all been there. So anyways, all of this, I mean, it's very hacky the way that we put this together, and we're working on trying to sort of, there are various open questions about the scalability of this type of thing. But I was very excited that we were able to make this work for this specific project that we were working on. And I'd love to chat more with people if they're interested in something like this. All right, so I'm going to just give a very quick example now of a sort of science use case of all of these aspects that I've talked about. And this is, again, the particular project is a couple of years old now, but it's sort of, there's very exciting potential for the future now that we have all of these different tools that I've talked about here today. So as a postdoc, one of the things that I worked on was looking at plots like this and trying to see if we could fill this in a little more, trying to push the detection limits in different directions. And one direction that I had some success was pushing the detection out this way to longer orbital period. And in particular, I searched some 40,000 stars for single transits. So the points out here would only transit once in the entire baseline of Kepler. And I put some points on the plot out here. And that's not really what I want to talk about today. I more want to talk about the fact that these were almost all single transits. So here's a plot of all of my discoveries from that plot. Almost all of these are just a single transit. And this is exciting because, like I said, TESS data are going to be released the day before Thanksgiving. And TESS's baseline is just 30 days, about a month. And so there are going to be a ton of interesting planets that just have a single transit. But there's also a huge amount of data that we're going to have to search. And so the scalable methods that I've been talking about here are going to be very useful when scaling this search up to something like TESS. And in particular, the model that I used in that paper was I used a realistic noise model that looked something like this, and I combined that with a sort of expert system where I wrote down all the possible things that could look like transits. And now that we have fast ways of computing this part and accurate ways of computing that part, then I think that there's a lot of potential for the future with this kind of thing. I'd love to chat with people about that. I don't really have anything concrete to say right now. Of course, this was my project, so this was all done on GitHub, this single transit thing. So if anyone here is interested in single transits with TESS, you could go and fork my repository and find all the single transits. It'd be nice if we talked about it too, but it's MIT licensed, so you can do whatever you want, really. But one thing that I wanted to comment, the sort of key aspect that I wanted to comment on here was that, again, we wrote the paper alongside the code for this. And it turns out that GitHub can be a really useful collaboration tool for writing papers as well. So I was able to convince my collaborators to submit their changes to the paper as pull requests We had discussions about the types of changes that they were making. And also we still have open issues about sort of exciting potential things that we saw in the data, and it's all of this is stored in the issues thread as part of the GitHub repository, not in like hidden in old emails that we'll never find again. And so this is useful. This was sort of an exciting thing about that project, and I think there's a lot of potential that you could benefit from this as well. Okay, so just to wrap up, I just wanted to I think I've driven home some of the themes, but I wanted to emphasize again that I think that in astrophysics, to push the boundaries of discovery and things like that, that it is worth thinking about developing new algorithms, and not just coming up with the algorithm, but actually implementing it and actually documenting it, and that can clearly have a huge impact. In particular, this really benefits from interdisciplinary collaboration. And so most of the projects that I talked about, I was working with people from other fields who had different things to contribute. Finding interdisciplinary collaborations and making them work is hard. I mean, I'm sure there are sort of intradisciplinary collaborations that are hard to create and maintain as well. And so it's definitely not a solved problem, and I don't know the answer. But it is something that I think is worth discussing and thinking about. And like I've said a few times, I think a lot of the success of the types of things that I've been talking about today comes from the open development practices and the documentation that comes alongside that. And I think that can go a really long way. And then the last thing I wanted to say is that almost everything that I described here was the key contribution was a piece of open source software. And alongside each of them, there was a paper that was published and went through the referee process, and that's so that's the way things work. But I guess one of the questions that I wanted to ask is this sort of the right way? Is this the way that things should proceed? And maybe that's true. Maybe it is the right way. But I thought it might be a food for thought. Is this a hack? Is this, is there some more efficient way that we could be doing this? So anyways, I'd love to have conversations with people about that. And just to wrap up, here are all the links to all of the GitHub repositories that I talked about today. All of my information is on my website. I like to answer emails and things like that if anyone has any questions about any of the things that I talked about that we don't have time for today. And thanks.
Questions for Dan? Yeah.
And what you said at the end I thought was really interesting about the difficulty of maintaining these interdisciplinary collaborations. But one difficulty might also be starting them.
Absolutely.
As I move in different directions, you're sometimes dealing with people where your language is different from theirs, and you're not sure you really understand what they're saying.
Yeah.
And maybe vice versa, I don't know. So can you say a few words about that? I mean, have you been in situations as you draw people into your collaborations where just setting up that common framework is challenging, and how did you deal with that?
Sure, yeah, so that's sort of the million-dollar question, and I don't have a sort of general, scalable answer to that question. So in practice, I was very lucky being at NYU as a grad student because the applied math department there is very strong, and I was able to sort of, with the help of my advisor, David Hogg, I was able to reach out to people, and the collaborations that worked were ones where we spent a huge amount of time together, and so part of that was sort of friendships were formed, and that sort of we learned to translate through that, and so I was privileged that I had that opportunity, and that's what worked for me. I'm still trying to figure out now what the sort of right solution is more generally. In my current position at our institute, we have several different centers, and one of them is applied math as well. And so I've continued going to their group meetings and trying to learn their language and inviting them to ours. And we'll see if any of that sticks. But it's a great question. I think we all need to think about it, but I don't have the answer.
Yeah.
So one of your final slides, you said that all of these projects, there's an open source code,
Yeah.
and there's a journal paper.
Mm-hmm.
And so I presume what one hopes is whenever anybody uses your open source code and they write a paper, they would cite your journal paper. Right?
Mm-hmm.
But this is not something you can enforce.
That's right.
So, yeah. Is
So-
this something that the community needs to discuss, or
Yeah, so
what exactly are you doing?
yeah, so I have lots of thoughts about that. So I personally have been very lucky in that people do cite the software paper associated with my projects. And you absolutely can't enforce it in a sense of like, you can't write legally binding text that requires that people cite you, but that's also true about other papers that you publish that aren't software papers, right? I mean, the community does try to enforce that, but maybe software is a little bit different. And one example that I can think of is AstroPy. So that's a huge project that's, sort of, that many people in astronomy use, and it's considered so fundamental that people often don't think to cite it. So I think there are lots of papers that use AstroPy, but since it's so much part of the foundation that there isn't sort of an individual associated with it or something like that, that people aren't so good about citing it. And so I think that probably it's at some level the responsibility of the editors of journals and the referees and things like that to recognize these kinds of things and try to encourage that. But and I think there is some progress in that direction. But, yeah.
This looks like an issue probably for the decadal survey.
That's a good
Software,
question. Yeah,
right?
yeah.
It's instrumentation.
Yeah.
Lots of things we just kind of use.
Yeah.
Somebody has put a lot of work into it,
Yeah.
and then
Yeah. And especially
they
the
need
things
to
that
be
are really
recorded.
fundamental, I think, are often overlooked. Yeah.
Daniel.
Just building on that, I think it would be much better if this kind of software citation were done through the references rather than through the acknowledgements.
Right.
There's a
Yeah.
proliferation of requirements about acknowledgements that I think are actually misplaced.
Yeah.
And it would be way better to push things into the reference.
Yeah. So the AAS journals do now support putting software citations in the references, and I at least sometimes get letters from the editors or suggestions from the editor that I'm missing certain ones. But yeah, I totally agree. Acknowledgement is not the right way to track it.
Okay, I think we have time for one more.
Yes, this is following Ramesh comment on the decadal. Your presentation is perfect for as an example for the decadal, because the decadal call is for the science student, and somehow the methods are not used to be treated scientifically.
Mm-hmm.
It's not research. This is our tool.
Mm-hmm.
And,
Well, I even
showing
use that
you
language in
done
my talk.
research, yes, so
Yeah.
I think you and people who work in that field, in astrostatistics, astroinformatics, have to show to the decadal review that we are actually doing research. It's not just something which we use on the side. And in your case, you have to do a lot of research in applied math and computer science, and even learning how to code and then apply to the data, and the outcomes are great for the community and for the research as a whole. So I encourage everybody to put this into the decadal papers behind.
Absolutely.
All right, well, I think we're at the hour, so let's thank Dan again for a great talk. Yeah. So
So as you can see, most of the periods are not very well constrained. Yeah, but it comes from the duration. So here, what I actually do is I actually fit a Keplerian orbit to marginalize over impact parameter that's invisible with some choice of but yeah, so that's what we do. Now, one thing is that if you have inner planets,
Whoops, sorry, didn't mean to cut you off.
Hopefully soon.
I'm becoming a Boston driver. I wasn't using my blinker.
Three-way Skype meetings with like her and our other collaborator who's at CCA.
Oh, okay.
So and they have their like trendy Skype room. I don't know if you know.
Trendy Skype room.
Yeah, they do. They like have like the instead of like
do you
Skyping
in your
on
office?
their laptop, they have like this video.
Like really good lighting.
Yeah. So they're like,
She's like Instagram.
video conference center.
You know, at some point pretty soon we'll
Yeah. So it's like hanging out in there, and then like
She's a
in
makeup
her
artist.
office.
Outside, like touching your
and see what the real world cancellation is. I mean, I think we'll start to see like a little dive, you know, cancellation.
I think I got places where you went. Arthur's house is like, just like, went on.